All right, in this module, this section I should say, we're going to cover a little bit on coding, the real basics of what code in Unity looks like and how to do just a couple simple things just to get you ready for some of the workshops. All right, the first thing I want to mention, Visual Studio Tools for Unity, VSTU. This is what enables you to use Visual Studio to edit and debug code, which you normally couldn't do just out of the box. There's a plugin that is set up for you automatically if you choose the option during the Unity install. If you happen to have Visual Studio on your system already, then you can go and download Visual Studio Tools for Unity, install it, and it will configure Unity to talk to Visual Studio for you all automatically. I recommend that much more so over MonoDevelop because, as we know, Visual Studio is an awesome IDE. It's my favorite one on earth to use, and it works great with Unity for developing and debugging your code. And it gives you shader syntax highlighting, code templates, which are really neat, IntelliSense as you'd expect, and full debugging support. And the debugging support is interesting because we saw that Unity runs in its own little virtual environment when you click play. So you can actually use Visual Studio to debug when you click play inside of Unity. That's pretty neat. And from a nutshell, basically, it acts as the bridge here, talking between Visual Studio and Unity. VSTU is a plugin that talks to this soft debugger, the mono soft debugger that Unity happens to use. So this plugin, VSTU, which is made inside of Microsoft by some brilliant gentlemen, they happen to write it, and it talks back and forth with Unity. Works great. Now, the programming model that we're going to talk about is game loops are per game object. And a game loop is when your code runs per tick. And really, a tick is how many frames per second your game happens to be running at. And that varies all the time. It could be at one moment running 30 frames a second, could be 60 frames a second, 120 frames a second. And that is the trick, to always get a good frame rate. And the way that you achieve that is either you have a simple game or you really highly optimize to make sure you're not doing things that slow your game down. It could be if you had a model that had too many polygons in it, that could slow your game down. There's all different tricks, and that's really the name of the game in game development, is to really optimize the performance and make a higher frame rate. Now, when you're dealing with programming, the constructs that you're used to in C#, so for example, lambdas using events, link, anonymous methods, classes, all those are supported inside of C#. Now, Unity uses Mono, so it's not quite up to date on all the same language features that you'll find in the latest version of .NET Framework, for example. But a lot of them are there, and Unity manages their own version of Mono, and so you can do some pretty cool things. But all the major constructs that you use. Now, it's a little bit different than enterprise development. If you happen to be used to enterprise development, there's little things you have to be aware of that might allocate. So, for example, iterators might allocate, I think, 28 extra bytes. And all these extra bytes per every single frame, let's say you're running 60 frames a second, can add up to eventually, when your game does, the runtime does a garbage collection. And then you might get a little stutter in your game while your game does a garbage collection. So a lot of it is about optimizing and caching references and not allocating memory where you don't have to do. All these tricks that you learn as time goes on. We're going to talk about the basics today. Now, the last point I have on the slide here is, do I have to code? There are third-party tools like Playmaker, which give you visual ways of writing code. They've essentially written the code for you, and you use these visual nodes, set the properties on these visual nodes. Those are some pretty cool tools. If you're not a coder, they're great to learn with. If you are a coder, they're great to prototype with. And you can also view the code behind them as well. There's also many asset packs available you can get from the asset store with code as well. All right, first let's talk about reading input. Under project settings input, Unity has an input system that basically says it's called horizontal. And so when you ask Unity what is the current value of horizontal, it's going to look at the left or right arrow keys or the A and D keys. These are common gaming keys. Think of ASDW as your gaming keys. And so horizontal is left and right, or A and D. And it's a value that will go between -1 to +1. So you ask Unity, input.getAccess, the word horizontal. And it matches this word right here with horizontal. It says, OK, well, let's read these input values. And it will be between -1 to 1. If you're not doing anything, the value will be 0. If you press to the left, it will be -1. If you press to the right, it's +1. And it actually sweeps through these values using this sensitivity value. That's how fast you're going to go from resting 0 to +1 or 0 to -1. So if you want your character, your input to automatically read 0 and then to 1 really fast, you crank up that sensitivity. If you want a really slow-moving object, you could crank down that sensitivity. So you're going from 0 to 1 kind of slowly. We'll debug these values so it makes a little bit more sense. Now, another way of doing it is this is just reading direct input, -1 to 1. What about keys? You can do input.getKeyDown, and that will return a true if you're pressing a particular key down. If you are pressing like get key down escape, that would return true. If you're doing input.getButtonDown, fire 1, that will map to your left mouse button or the control button. If I look inside of Unity and go to Edit, Project Settings, Input, right there, fire 1 is actually the one that opens up by default here. The name is fire 1. The positive button is left control. My left control button will essentially give me fire 1. Or my first mouse button, mouse 0. So if I ask Unity for fire 1, if either of these keys at that particular frame happen to be set, then it will return true. And then I can do whatever action I want for fire 1. So that's how you read input. We'll look at an actual live demo of this in a second. The next common operation that we'll do is finding game objects. This is huge. You do this all over the place. Now, when you want to communicate with another game object from somewhere else in your code, there's really two ways of doing it. One, you either ask Unity for that game object. Say, hey, Unity, find me the game object that has a tag of player. Or find me all of the game objects. Notice the S here, the very slightly different API returns a collection of all the game objects tagged zombie. Or maybe find me a single object named Bob the Zombie. Now, this is pretty slow, and this is usually recommended you don't use this technique here. We usually don't look for a game object by name. If we have multiple instances of an object that we create at runtime, dynamically on the fly, the names of the objects can change. It could actually be Bob the Zombie (clone). We typically don't ask for an object by name. This is the most common. You ask for a game object by tag. It's optimized. It only looks for the game objects that have tags set on them. Remember, that was that little drop down right on any game object right here. That's how you set a tag. So if you ask for the game object with a tag player, you will get a game object return here that represents that player, or null if it can't find that. Another way that you can set up references between game objects are you define public variables, and you can do dragging and dropping. We'll look at that later on. Now, moving game objects, another very common operation. The best way to do this, the most performant, so to say, is to move it with physics. And it's a little bit of the cart before the horse because we haven't talked about physics yet, but a component on a game object for physics is called a rigid body. One of them that you can use is called a rigid body. So if you want to add a one-time force to an object, you can basically just say add it to that object to the right, vector 3.right, times some horizontal input that you just read. Or if you want to act like you kicked an object, you could say add force and give it a vector of a direction, maybe 1, 5, 8, and then you give it some value of force. The most common way, and the way that we'll look at very shortly, and in most of our labs, we actually tell the rigid body, the physics component, that we set a velocity. It's a point-in-time velocity. And in that, you just specify what the velocity is in meters per second. So this is some read-in value times a speed, 20 meters per second. Remember, our horizontal input we're reading in is -1 to 1. So if we're all the way to the right, we're going to be moving at 20 meters a second. And if we press all the way to the left, it's going to be -1. So we're going to be going at -20 meters a second, which is going to be going to the left. Very common way of doing it. Now, less common way, it will work. This used to be a huge performance issue. They've changed at Unity 5. You typically don't do this, although you can. If you don't have physics on your objects, you can just move their transform. Recall that the transform is this property right here on a game object as a position, rotation, and scale. You can just, at runtime, change these positions. So for example, on this vamp kid, right, if you change the X value, he moves. The downside of doing that is you can actually skip physics interactions. If you want to do that, that's fine. If you just want to move an object and not care about anything, you can absolutely do it that way. But if you want it to interact with the real world, then you want to use rigid body movement. And there's several other ways too, outside of even just using velocity, that you can move a rigid body. This is only used when you know you don't want to use physics for some particular reason. Maybe you just want to have an object move from point A to point B and not care about physics at all. All right, let's look at the basics of Unity code here. Inside of Unity, the way that you, let's go under training, the way that you create a script is you right-click and you say create a C# script. Now, it's waiting for you to rename it. Whatever you rename it to will be the name of the class. And the name of the class must match the file. So, for example, my first class. Notice it creates it called my first class. Let's open that up, double-click on it. Opens in Visual Studio. My first class inherits from mono behavior. Mono behavior means, all right, this is going to be assigned to a game object, and as such, we will understand what a game object is. Everything is about our current game object. So when we start up, we get two methods here, and there's a whole bunch that we can integrate with. This is our startup. We don't use constructors. Game objects don't use constructors. Let me specify that again. We use start code here. Now in here, we could find another game object. Oops, another game object. Or, in this case, let's just do a debug.log. My name is lowercase g. I can really say this, but we don't need this. But just to see the properties that show up, this dot show me the game object here. My IntelliSense is acting funny. Game object dot name. So this particular game object that we're currently assigned to, we can reference its properties by saying game object dot name. And that will refer to whatever game object our code is assigned to. So let's take this code. Notice we have a little bit of a delay because it was compiling our code. Let's take this code and assign it to VampKid. And the way that we do that, we have four ways. We can drag it there, we can drag it here, we can drag it in this little area here, or we can add component and specify it here. My first class shows up there. I typically just like to take my code and drag it onto my game object. And there it is, my first class. Now when I click on play, debug.logs will show up in the console. We're seeing a couple warnings just because of the current version of Unity. Let me not maximize this on play. We're seeing a couple warnings because of the version of Unity. There's been some minor changes. So in this code base that we're working on, there's just some non-error warnings. Now, right now, notice this got called one time here. My name is VampKid, and showed, if I double click on it, it takes us right to the code that did the debug logging. My name is, what was the game object.name? VampKid. It got called one time. Now, update is called every single frame. Debug.log updating. Now, if we go ahead and run this, give it a second to compile, we'll see that updating code is going to get called over and over and over again. We can see right here. Updating is getting called 80, 90, 100 times a second. Why is that? If we look at the stats button here, we can see because we're running at about 40 frames a second, 35, 40. It varies all the time. And that's how many times per second we're writing that debug message out. So that's the basics of a code file. Now, all the various code methods that you can use, using Visual Studio tools for Unity, it's easy to complete our methods for us. So if you forget the Unity-specific methods, you can right-click and either say Implement Mono Behavior or Control-Shift-M. And that will show you the whole list of Unity-specific methods that this will understand here. And I think because I know what I did, I will come back to this momentarily because what we did was I had a disconnected instance of Visual Studio running, so that's why we're seeing just a little bit of the quirkiness there with our IntelliSense and everything else. So I'm going to go ahead and kick this off again, launch this. Now, the perception is this takes a little bit longer just to load Visual Studio this way, and it's only because the way that this interface works as it stands today is there's no, you don't see the Visual Studio splash screen and all of the initialization happen. It basically loads up when it's just about ready. So it seems like it takes quite a bit longer because the perception is, you don't have any splash screen there. So we'll give this a moment to start up. While that happens, let's talk about what we're going to do next. We're going to take our read input code, and we're going to see what those values look like. In other words, that -1 to +1 as we use a keyboard. So the character in our games, we're going to be moving left and right. And so we're going to read that left and right input and map it to that actual character. Okay, give us a second to initialize here. Do you want to fix your character return line feed? Sure. And something's still acting goofy on my system here. So I will get that figured out so I can come back to this and show you momentarily what is going on here. Meanwhile, let's go ahead and continue with the code that we're going to look at here. All right, so this class here, simple move. Actually, let's go to reading input first. This is the simplest one. Every frame, we're reading our horizontal input, our vertical input, and we're just going to debug it out. So get access horizontal, get vertical, and debug it out. Let's go ahead and do that. I'm going to take, that's under scripts, reading input, and I can drop this on any particular game object. Let's hide this. So reading input, I can put it on the zombie, although it doesn't matter. Any game object can read input. It doesn't matter what object we actually have it on right now. I just dropped it on the zombie because that makes sense. We'll move the zombie. Click on play. All right, now in the console here, notice horizontal is 0, vertical is 0. Now, let's go ahead and click in this window. I'm going to remove the collapse here. Hold the right arrow down, let go. Notice it ramps up to 1 for horizontal and then goes back through the values to 0. Up, down. Let's go negative. I'll press the left arrow. -1 and back to 0. It happens pretty fast. That's because our objects will slowly move faster or not. And you can see actually my little vamp guy here is actually reading that input. Why is our vamp kid reading that input? Because vamp kid has the next very, very simple one on it called simple move. Now simple move gets our rigid body component. We're going to talk about physics shortly. Just know that this is the component that gives our object mass. Now we ask for it when we start up. This is extremely common. This is very, very common. We are asking Unity to give us the component on our current game object for the rigid body 2D, and then we store that in a variable. We don't want to have to do this every single frame. We just ask, when this object starts up, give me the rigid body physics component, because every frame, we're going to read some input and apply it to it. Now, you might have noticed that before we had a fixed update function, and now we have this, you notice before we had an update function, now we have a fixed update. If we look, there's our Unity methods, they showed up here. This was Control-Shift-M. This shows us all the Unity methods that we can integrate with, and Visual Studio Tools for Unity will generate these all for us. Now, update gets called every frame. Why is there a fixed update? Fixed update is tied to physics. The simple rule is if we're moving an object via physics, you do it in the physics update. This is tied to the physics engine, whereas update, this is tied to what you see on the screen. Fixed update is from the physics engine, which is either Box 2D or NVIDIA Physics, depending if you're doing 2D or 3D. So again, two different purposes here. Update is just called every single frame. You know, your game's running 40 frames a second, 50 frames a second. Here, when I'm moving an object, we are reading the input, the horizontal, and now we are calling our local transform. We're saying transform its direction. And what this will do, this will give you a directional way to move an object. In other words, essentially we're saying give us a vector back. Give us a point that represents an arrow back to us that we're going to assign this velocity. Velocity really uses a value in meters per second. So what we're asking it is, hey, give us some object, maybe 3, 0, 0, which is really going to be telling our velocity that we're going to be moving at 3 meters per second in the x, nothing in the y, and nothing in the z. Now, this here, we're just reading in our horizontal input. Remember, that's -1 to +1. We have some speed multiplier, so we can make it go a little bit faster. That's just defaulted to, it's a public variable, we defaulted to 75. So this is going to be between -75 and +75 meters per second. Well, that's pretty fast. We multiply it by time.delta time. This is a new concept. You'll see this quite a bit once you start doing Unity development. This is the amount of time it took the last frame to complete. This is a very common way to smooth out your operations. Why do you want to do that? Well, think about this. If I have something like this, and now I'm running on an extremely fast system that is running so fast, my character is going to be moving a lot faster across the screen than it is on a slow system. And so when you introduce time.delta time, these are little values like 0.01, 0.013, and that will, over the length of a second, they will all sum up to 1. So it's essentially the portion of a second the last frame took to complete. And so when you multiply this, it essentially smooths this out. So no matter what system you're running on, that object will be moving at the same speed, assuming you're reading the same input. Very common way in these loop-based systems that can operate at different speeds of making sure that you have consistency across those systems. And faster systems don't run faster. In other words, a character moves across the screen at the same speed. All right, so that's the basics of that. Simple move, reading input. And lastly, let's show a simple follow. Simple follow asks for the rigid body of whoever we're on, and then it lowers to physics components. And what we will do is we do another operation called raycast. And so what's going to happen here is every 2 seconds, the zombie, let's go ahead and take the script and drop it onto our zombie. Every 2 seconds, the zombie is going to shoot an arrow out. Let's see which directions we do this first. Every 2 seconds, we're going to shoot, oh, I'm sorry, every frame, every physics frame. What is a physics frame? Our physics frames by default run 50 times a second. How do I know that? If we go to Edit, Project Settings, Physics, and our time step, actually, that might be under our editor. Give me 1 second here. Time, that's it. Our fixed time step is, this is 0.02, which is 50 frames a second. Our update functions can vary all the time. Fixed update is 50 times a second, and Unity will do everything it can to make sure that gets executed 50 times a second. It's so you have some consistency when you're moving your objects and doing physics. Physics operations, you want to be consistent. You don't want to have one force applied at a 1/4 second and a different force applied at 3/4 of a second. You want some way that you know these are consistent every second, 50 times a second. So 50 times a second, we're shooting an arrow out to the right, shooting a little invisible arrow called a raycast to the right. And we're asking for whoever it hits that has a physics object on it called a collider. So it's shooting an invisible arrow called a raycast. Now the code looks just like this. Physics.raycastAll means shoot an arrow out to infinity to the right and tell us who we hit. In this case, I'm actually filtering out by a layer, which is what this little syntax means. The actual vamp kid sits on his own layer, layer 8. How do we know that? Well, I set it up like that. If we look at vamp kid, I define a custom layer, layer 8, called player. Vamp kid is on layer 8. It's right here in the dropdown, player, which we just saw is 8. And the reason we do that is for performance. We're asking the zombies to shoot an invisible arrow out to infinity and tell us whoever they hit. It could be hundreds of objects. the fact that we have just the vamp kid on that layer is very performant. He's the only object that will be found on that layer. We shoot an invisible arrow out, and if we find an object, then we know that we've hit our vampire, and we know that we can now follow the vampire. We can move our current transform in the direction of that vampire. Transform.transform direction. We can either move positive, in order to move to the right, or if the vampire is to the left, we can move to the left. We multiply it by -1, and we're going to move to the left. Remember, these are vectors. These are x, y, and z values. So this is going to move us to the right. That little bit times 75, or this negative bit times 75, and 0 and 0. We're not going to move in the y or the z. Now, on our renderer, we can flip our zombie, right? We might need to move to the x or the y, and that's what this guy does. See our zombie? We just flip it. Very easy. If our vampire's on one side, we're going to flip. If it's on the other side, we're going to flip back. Now let's see what this looks like in practice. As soon as we click play, we can see our zombie is immediately following our vampire. Let me move the vampire out of the way. Let's zoom in too. Let's move the vampire out of the way so he will no longer get hit by that invisible arrow. And look at, immediately he stops. Now every 50 times a second, that invisible arrow is shooting out to the right. Now we just hit it. Gone, let's come to the side. So that's how we do object following. And you'll see that quite a bit in the lab when any enemy character needs to find the main character. And there's different ways of doing this. In this way, it's just a simple case of shooting out an invisible arrow and determining which direction we just shot the arrow out in, and making sure that our current object moves in that direction a little bit. When you first see these API calls, like transform direction, they look kind of strange. When you see them time and time again, they're very common calls that you see over and over again. And they start to become pretty familiar. All right, so a couple of new concepts here. We talked about the fixed update function, which happens 50 times a second for physics, and we're going to touch upon physics again shortly. And we only did it in this case because that's when we were moving an object. We were using physics to essentially set our velocity 50 times a second. We saw it with creating a basic code file. You create it. It creates a couple methods for you by default. There's start and update. You don't have to use them. You can use Control-Shift-M for Visual Studio Tools for Unity, which we're going to use in the physics section as well to add our code for us, to show us the code methods that we can integrate with Unity. If you remember off the top of your head, you can type them in. If not, you can just use these Visual Studio Tools for Unity. So hopefully that got you a basic idea of how the coding works inside of Unity. It is per game object. We drag and drop it onto a game object. The instance that code is running in it is just for that game object. That game object can refer to itself. It can get its own components by calling get component. And it can find other game objects by saying GameObject.find GameObject by tag, or GameObject.find GameObjects by tag. So it's a pretty simple API to use. Again, it's probably all new, but you'll see this over and over and over again in our workshop. We'll see you next section.